So if you remember our discussion of metals, we talked about how metals are able to conduct electricity. And part of what we talked about there is we talked about two lithium atoms. So you have a lithium atom here, you have a lithium atom here, and what we do is we allow molecular orbitals to be formed. And when the molecular orbitals form, they form like this. And so we always draw this gap that looks like this. I never really talked about, though, what makes the distance of this gap what it is. And in part, what it has to do with is it has to do this due to the stability of the electrons when they're between the two atoms versus when they're outside the region of the two atoms. So what makes that more stable, right? And we've talked about this before in maybe some different contexts, but it has to do with the nuclear charge. The more positive charge that's exerted by the lithium atoms, or the atoms in general, because it doesn't have to be just lithium, the lower in energy those orbitals will drop. And if, just thinking of conservation of energy, if it becomes more stable of an interaction when it's inside the region, it becomes a less stable interaction outside the region. So this gap between these two increases in size as the nuclear charge can more effectively stabilize the electrons between the two atoms. So this is why when you look on a periodic table, what we find is that good electrical conductors are all in this left-hand side of the periodic table. As you go from left to right, and mostly thinking about main group elements, not necessarily these transition elements, but thinking about main group elements. So groups 1, 2, and then 3A, 4A, 5A, 6A, 7A, and 8A. What happens is the electrons get stabilized by the increasing effective nuclear charge of the atoms. So lithium and beryllium are metals. Boron is not a metal. It's more in the semi-metal class. And then carbon is a non-metal. Again, when you're looking from top to bottom, like this, right, the electrons get further and further away from the nucleus. And the result is the gap between the lower bonding orbital and the anti-bonding orbitals decreases because of the less effective overlap of the electrons between the two atoms. Less stabilization by the nuclear charge, simply because they're getting further and further away from the nuclei. So the result is small differences in bonding and anti-bonding orbitals down here causes these to be metals, and then high differences between the bonding and anti-bonding orbitals here cause there to be a large difference. So let's go back to looking at this structure for lithium that we were talking about before. What ends up happening when you bring in more lithium atoms, we think about a large sort of interaction between all the atomic orbitals of the metal. Mostly we're thinking about it sort of in two dimensions along a line. But if you had a third one, for example, what you end up getting is a bonding orbital, an anti-bonding orbital, and then what's called a non-bonding orbital. Symmetry makes us have one in the middle because we can't break the rules of conservation, basically. So if you add extra, right, atoms into the mix, then what you end up with is getting something that looks like this. And the high level and the low level are all determined by the stabilities of the orbitals. So there's a distance between the top and the bottom that you can have, and as you add more orbitals into it, in this particular instance, you'll get something that looks like this. So this would be 3 orbitals, 4 orbitals, 5 orbitals. And eventually, what we came to the conclusion would happen is you'd end up with a whole bunch of orbitals. These are all anti-bonding orbitals. And then you'd have all bonding orbitals. The result is there's almost no energy gap, or there's zero energy gap between the orbitals of the lithium atoms as you start looking at a chunk of lithium metal. And so we talked about this being the conduction band, and this one being the valence band, because that's where the valence electrons will be found. Okay, so this is what we call band theory, and really what we think about is orbitals being groups of bands like this, okay, which are of interactions of atomic orbitals to create molecular orbitals. So, in essence, electrons will occupy the lower level, right? And so this becomes our, like I said, valence band. But if this valence band is full, there's no room for the electrons to move, and so this is why this is called the conduction band. If you can take electrons out of here and put them up into this band, then they're able to move freely amongst all the other atoms. So, the picture on the left is from your book. This is essentially the description of lithium. We have one atom of lithium, right, and then two atoms of lithium. So you have a pair of electrons in here. Then you have three atoms of lithium. They show some growth in the energy difference between the states, but what you have to do is you have to disperse all the energy levels between the high and low energy molecular orbitals. In essence, this creates the bands that we were talking about. And in lithium, the valence band is fully occupied, and the empty orbitals of the conduction band are where electrons need to go for electric current to be transmitted. So if the energy difference, right, between the bonding and anti-bonding orbitals is great, you can imagine a situation where you create a gap between the valence band and the conduction band. So this is what's happening when you're looking at elements like carbon, nitrogen, oxygen, fluorine. The difference in energy between the bonding molecular orbitals and the anti-bonding molecular orbitals is so large that it creates what's called a band gap. So the band gap actually keeps electrons from moving because the valence band is full. Electrons can't jump to the conduction band, and without being able to going up into the conduction band, you can't conduct electrical current. So these are the insulators, and then there's semiconductors, right? Conductors, semiconductors, and insulators. In semiconductors, the band gap is just not that big, and so we're able to, using either electrical energy or photon energy, able to transmit an electron or promote an electron from the valence band to the conduction band, and once you've done that, the electrons are free to move through the conduction band. So to somewhat summarize what's going on here, if you can get electrons to go from the valence band to the conduction band, then electric current can flow. And this is true for both semiconductors and conductors. It just takes more energy, a higher voltage on a semiconductor to promote electrons to the conduction band in order for electrons to flow. It turns out semiconductors can also do this, though, if you get them too hot. And so people who play with computers are familiar with, just trying to get rid of heat, dissipating heat from their processor. And what we do is we stick big fans on top of the processor. The reason for that is if you don't keep the semiconductor cool, or reasonably cool, they can get pretty hot actually, but reasonably cool, what happens is electrons begin to promote because of thermal energy, and then the processor can no longer process information correctly because now it's just conducting electricity all the time. So one of the big challenges in semiconductors is being able to dissipate this heat quickly in order for to give you sort of a better performance over at higher speeds, because the higher speed that you run your semiconductors at, the more electrical current you pass through them, the hotter they'll get. So if you can cool your semiconductors, you can get higher bandwidth performance through them because you don't have to worry so much about the thermal promotion of electrons to the conduction band. So in general, elements that are used for conductors have low electronegativities. Now I just stuck this in here because electronegativity is an indicator of effective nuclear charge. And so elements who stabilize the electrons in the bonding orbital strongly, those are what we call insulators, and the ones who do it relatively weakly, these are electrical conductors. And that goes along with the electronegativity. So it turns out metals are good conductors of electricity because of this, but it's also the reason they're good thermal conductors, because it turns out the electrons can transport that thermal energy through a crystal lattice very effectively. So what we're going to do next is we're going to look at it in a little more detail about the band gap between the valence and conduction bands. In particular, we're going to be looking at semiconductors. So when we look at the band gap for carbon, what we find is that the gap is 5.5, what's called electron volts. Now that's not really that useful to people, but I'll just show you how to do this conversion real quick. I don't know why the book decided to use electron volts here, to be honest, and not also include this information. But 1 electron volt is the potential energy experienced by an electron in a 1 volt field. And so what that turns out to be, I know, right? That turns out to be 1.6022 approximately times 10 to the minus 22 kilojoules. I like doing it in kilojoules because as chemists we tend to think in joules and kilojoules. Well, if you have a mole of these, so we multiply this by Avogadro's number, that tells us how much energy we have per mole of electrons moved. And this is a number that makes a little bit more sense to us in terms of like calculations. This is 530 kilojoules of energy approximately per mole of electrons. So that's actually a pretty big gap in energy. You have to put in 530 kilojoules into a mole. And that classifies carbon as an insulator. Just for sort of comparison purposes, they do calculations based on the energy difference between the conduction band and the valence band, and the energy difference of 5.5 electron volts turns into this number. It's about 10 in the conduction band. We have about 10 to the minus 27 electrons per centimeter cube. So these are electrons in the conduction band. Okay, so that's really zero, right? There's almost no electrons in the conduction band. And the result is carbon is an insulator because in order to have electrical conduction, for example, between in pure carbons in diamond, right? What you have to do is you have to put electrons into the conduction band so that charge can move. Okay. Now, in silicon, which we call a semiconductor, this 1.1 electron volts corresponds to about 107 kilojoules. I'm going to write it over here per mole. And then when we look at the number of electrons in the conduction band, it's on the order of 10 to the 7th. Or sorry, it's 10 to the 9th. So now there's 1 billion electrons per centimeter cube. So I'm going to say E's per cm cube now. Now, for germanium, which is also a semiconductor, so with this many electrons, that sounds like a lot of electrons. I'll show you in a second, though. It's really not that many. This sounds like there's a lot of electrons in silicon in the conduction band, but if you look at germanium, right? Germanium is small difference here in band gap. This corresponds to 65 kilojoules difference between the conduction bands and the valence bands. The number of electrons that we find is now on the order of 10 to the 13th. So for tin, the energy density, the band gap energy difference only comes out to be about 7.7 kilojoules per mole. And the charge carrier density grows exponentially. So by the time we get to tin, essentially what we're looking at is the density of valence electrons. And it's on the order of 10 to the 23rd. So basically every atom has more than one valence electron. And as a result, there's a very high charge density charge carrier density in conductors. So tin and lead are essentially both conductors. Essentially, it's all the free valence electrons. So you can see, like in silicon, even though it says there's 10 to the 9th, that's not very many in comparison to the 10 to the 23rd. But these are conductors, and silicon and germanium are classified as semiconductors. So how do we use semiconductors? It turns out the energy gap in silicon and germanium are still fairly large. And so what they turn to is they turn to something called doping. And I'm going to give you a slightly different explanation of doping than what your book does, okay? But this is our sort of classic valence band, conduction band. And what we can do is we can put in, for example, phosphorus. And phosphorus has an energy in between the conduction band and the valence band. So phosphorus orbitals are in this region. And if you think about phosphorus's structure, right, it has extra electrons in it. It always has that lone pair. So what happens in phosphorus is that you can use a small amount of energy and you can promote an electron into the conduction band. And then let's say this is the positive voltage here and a negative voltage here. What can happen then is the electrons can flow in this direction. But the key is that we're having electrons do our work for us. And so these have negative charges, right? These are known as N-type carriers or N-type semiconductors, because the charge carrier is a negative charge over here. Now, so we have N-type and then we have P-type. And the P-type, you might guess, is because the charge carrier is a positive charge. And the way we do that is we use group 3 elements. And gallium in particular has an energy within the conduction band. So here's a gallium, right? But it's electron deficient. And so now what we can do is we can take an electron from the valence band and promote it into the gallium. Well, that gives the gallium a negative charge, but what does it leave behind? It leaves a space which is called a hole. And the hole has a positive charge because it's basically the absence of the electron. Now, the electrons in the gallium are not mobile. The gallium atoms can't transfer electrons to other gallium atoms. So what ends up happening in a P-type semiconductor is if I have a positive over here and a negative over here, what ends up happening is the hole ends up moving through the valence band. You could think of it as electrons still moving towards the positive, but the way it's generally viewed as if the hole, right, gets filled in and is moving to the right as electrons move into it. So charge is actually carried by the promotion. You promote the electron into the gallium, the electron deficient, right, substance in the gap, and then the hole is what moves. And so we call this a P-type because charge is being viewed as being carried by the positive charge, which is really just the absence of an electron. Maybe one other thing is important to realize. When we have semiconductors, the way we get them to conduct electricities is to actually we have to promote this electron from here to here, let's say. The way that's generally done is we actually apply voltages in two directions. So we can create an electric field like this, for example, in one direction, and we can create a secondary electric field in this direction. This electric field is simply to promote the electron into the gallium in this case, in which case allows electrons to flow, or a charge to flow through the holes down here. And then this charge is what we're using to actually move the electrons through a wire, for example. So we use a charge here to promote the electron and a charge here to move the electrons. Same thing happens in a N-type semiconductor, is we can use a charge here and pull the electrons from the phosphorus into the conduction band, and then we have, that's just an electric field, and then what we can have is electrons conducted through the conduction band. So here we have an interesting question. It says, which element would you dope into germanium to create a p-type semiconductor? It's not really important that it's germanium, because germanium and silicon are really the only two elements that are commonly used as semiconductors, except for some synthetic materials that are being created. But what you're really paying attention to in this question is that it is p-type. So you can think of it like this. I have a valence band and a conduction band, like that. And I want to have a p-type semiconductor, which means I want to have positive charges in this layer, right, to move the electrons. In order to do that, I've got to take an electron out of here and put it into an element that has an energy in between the valence and conduction bands of germanium. So what kind of element, right, would fit this criteria? And it would have to be something that is electron deficient. So if you remember when we were drawing our Lewis structures of compounds, the only group that is typically electron deficient in its Lewis structure are those in group 3A. For example, boron, right, is an example of an element that typically doesn't satisfy its octet. But the reason that makes boron useful is because you can promote an electron into it in a semiconductor. So, hang on. We look at our periodic table. Oh, so I wanted to put here electron deficient. So we're looking at group 3A or 13. So looking at the periodic table, like that, right? This is group 13 or 3A. So in principle, it's going to be one of these down here, closer in energy to germanium. And so we could put gallium, indium inside germanium potentially and have a semiconductor that creates a hole in the valence band so that the electrons can move. So in our choices, we have indium, as one of our choices. So that's most likely the dopant for the germanium to make the p-type semiconductor. If it has extra electrons, then it would make an n-type semiconductor.